Welcome to your e-learning video. What we're going to look at in this video is how to write the equation of a least squares regression best fit line. Okay, we've been talking about best fit lines. We've been using equations for best fit lines to make some predictions. Today we want to actually figure out how do we write that equation of the best fit line. And there's two different possible best fit lines that we could look at. One of them is very easy to find, the other one's very difficult. So we're going to look at the one that's very easy to find. But here's an example of those two best fit lines. We have some data here that represents the financial aid that a student gets from a university versus their family income. And so that's what we're looking at. There's been two best fit lines that have been plotted up here. There's a solid line and there's a dotted line. The dotted line is the best fit line that results from minimizing the residual values, the values that are different between the y value and the predicted y value, the observed value and the predicted y value. So for example, if we pick a point here and we were to subtract the y coordinate for that point that we observed minus the y coordinate we would predict from the best fit line, that residual value, the dotted line represents the line that creates the minimum value for all those different residuals. The solid line represents the least squares regression model. And basically it does something very similar. It takes the residual values, but it minimizes the square of those residual values. So in other words, if the difference was 2, it's looking at the square of that. It's looking at 4. So it takes all the squares of these values and then minimizes all those values put together. Now we're going to look at the least squares regression model for a couple of reasons. First of all, as I already said, it's the easier one to calculate. And so it's always nice to stick with the easy version. That's what we're going to go with. The other reason why it statistically might be a little bit better is because it makes points that are farther away, it makes them a little bit more significant in our calculation. We of course want to minimize the ones that are close, but we definitely want to minimize those distances that are farther away, because sometimes those distances that are farther away, if they're twice as far away, they may be more than twice as significant. That error may be more than twice as bad if it's twice farther away. And so taking the squared values into account will take into account that discrepancy. So that's why we use this least squares model. Now, to find the actual equation for the best fit line using this least squares regression, there's two formulas on your AP formula sheet that are going to come in handy. And they're in the top section of your AP formula sheet. These are those two formulas. One of them says y bar is equal to a plus b times x bar. And the other one says b is equal to r times sy over sx. One important thing that I want to point out to you is we're used to seeing the slope-intercept equation written this way, y equals mx plus b, where b is the y-intercept. When we talk about least squares regression, b is not the y-intercept. B is actually the slope. Okay, here's our value for x that we're substituting in. B is the slope in this problem. So keep that in mind, that when we're finding b in this problem, it's not the y-intercept, it's actually the slope. It's just from a long time of figuring this, they use the values for a and b instead of using m and b, and then that value for b gets switched around. So you just want to kind of keep that in mind, that when we find b with this formula, we're actually finding the slope. All right, so let's practice doing that, using those formulas to find our equation for our best fit squares line. So to start with, here's some data we've looked at before. We've got trips to the water fountain, we've got trips to the bathroom, and we've worked with this data, and we found that the average value for x is 4.33 with a standard deviation of 2.65. The average value for trips to the bathroom is 4.44 with a standard deviation of 3.09. We've also calculated before the correlation coefficient, r, is 0.741. So we're going to use this formula to find the slope of the least squares equation. All right, so for r, we're going to substitute in 0.741. For the standard deviation of y would be 3.09. Standard deviation of our x values would be 2.65. So go ahead and substitute that in and find your equation, or find your value for the slope. All right, so hopefully what you did there is you put 0.741 times 3.09 divided by 2.65. Just putting that into your calculator, hopefully you get 0.864. So that's our slope. And so at this point, for our equation for our best fit line, it would look something like this. Our predicted value is going to equal 0.864 times whatever the x value is. Now we need to figure out what that y-intercept is. We need to figure out what that other number is. And so that's where we're going to use the second formula here. Y bar is equal to a plus b times x bar. So again, going back to the values, we have values for y bar, we have values for x bar, we now have a value for b. So go ahead and substitute that into the equation, and it looks like this. Now we're going to solve that equation for a, which will be our y-intercept. So go ahead and solve that equation. What do you get for a? Okay, what you should have found for A was you should have gotten the number 0.699. And so now that we have that equation for A, we can substitute that into our least squares regression line where we've got this blank here. And what we're going to end up with is 0.864x plus 699. Now, that equation is slightly different than the one I showed you previously. Again, I don't know where I made my mistake at, but this is the correct value based on this data that we've accumulated here. So now if I wanted to make a prediction for any other number of trips to the water fountain, I could substitute in my value for x, and I could get my predicted value for y. So that's how we're going to find this least squares regression equation. So even though it's pretty complicated to think about going through and finding all those residual values and squaring them and then finding something that's going to minimize the overall total of that would be a really complicated process. The actual way to find the equation of the line boils down to some pretty easy calculations here. All right, so look at this last example for today. And here we have a grocery store that has selected 20 different customers and has asked them when was the last time you came to the store, and then has observed how many items they've bought, and they've made a scatter plot comparing those two things, expecting that the number of how long it's been since they've been to the store the last is going to influence the number of items they've purchased. So what I want you to do first is go ahead and determine the equation for the line of best fit for that equation. So start by finding your slope and then find your y-intercept. So go ahead and find your value for slope. What do you get for your value for slope here? Okay, so what you should have done is you should have used that formula b is equal to r times sy over sx. And so if we do, we've got our formula, our value for the correlation coefficient of 0.787, our value for sy and sx, and we get 4.21. So our slope for our least squares regression equation is going to be 4.21. Okay, now use that and figure out what the y-intercept would be. Find that value for A. Okay, so when you find the value for A, you're going to substitute in y bar, you're going to substitute in x bar, and you're going to substitute in the value for B you just got. And so hopefully you got 3.27 for that y-intercept. So our equation for our least squares regression line would be y hat is equal to 4.21x plus 3.27. Or if you want to put it in the other order, that's fine too. Y hat is equal to 3.27 plus 4.21x. So these values that we have are our slope and our y-intercept values. And so the significance of those values, that's the second part of this question, is what's the significance values for A and B? So slope, remember, is the rate of change. Another way to think about it is slope is the average amount that y is going to change when we increase x by 1 unit. So in terms of our graph here, when we increase the number of days since the last visit by 1, then this would be the amount that the number of items purchased will increase. The y-intercept is going to be the value, or the average value of y. I should have put average there. The average value of y when x is 0. So in this case, the average value for number of items purchased when it's been 0 days since their last visit to the store. So again, just kind of reiterate on that, the slope is going to mean that for each day since they've been to the store, people buy 4.21 more items. So every day that they've not go to the store, they're going to buy 4.21 items the next time that they go. And then the y-intercept, that 3.27, means that if it's been 0 days since they've been to the store, they're still going to buy 3.27 items when they come in. So maybe you went to the store earlier in the day, you come back in the afternoon because you forgot something, you might go in, you might have to buy just 1 item or 2 items or 4 items or something like that. But on average, it'd be 3.27 items. But for every day it's been since you've gone to the store, when you go back, you're going to buy 4.21 more items on average. And so that's the significance of those two numbers that we just calculated there. All right, so hopefully that makes some sense to you. You're going to practice finding these least squares regression lines today in your assignment. Again, if you have any problems, make sure you reach out to me via email or via Canvas Messenger, and I will try to get back to you as soon as I can with that. All right, good luck.